Some organic solvents absorb small amounts of water when they come in contact with the aqueous layer. A really good example of this is diethyl ether, which absorbs about 1.5% of its weight in water, which doesn't sound like a lot, but later on, if we evaporate that diethyl ether, we would be left with droplets of water. When an organic solvent contains water, we say it is wet. Now, in our everyday life, when something is wet, say for example, we take a shower and get out of the shower and our body is wet, we take a towel and remove the water on our body, and we say that we are drying off. In general, the process of removing water that is undesired is called drying. Therefore, we use this same terminology when we refer to removing water from a solvent that we don't want to have water in it. We say we are drying the solvent. It's important to note that drying a solvent is not the same thing as evaporating the solvent. When we evaporate a solvent, we remove all of the liquid and leave behind only whatever residues are in the solvent. In order to dry a solvent, we generally use something called drying agents. Drying agents are typically solids that are insoluble in our organic layer, but that absorb water to them. Very often we use inorganic substances that are able to create or absorb waters of hydration. Examples of drying agents that are commonly used in organic chemistry include magnesium sulfate, sodium sulfate, and calcium chloride. Each of these has its strengths and weaknesses, and so the solvent the solid that would be used would depend on those strengths and weaknesses and what was available. In order to dry then, it's pretty straightforward. We transfer our solvent or solution that we want to remove water from into a clean, dry container. We want to make sure that we don't add more water by having a wet container. A small Erlenmeyer flask works usually very well for this. We then start adding the drying agent in small portions, typically using a spatula, and we then swirl that liquid. What we should see is, when we add the drying agent, we should see solid mixed in with the liquid, the solid drying agent. We don't expect that drying agent to dissolve. We then swirl that mixture, and what we observe is, if there is water in the organic solvent, it will absorb into the drying agent, and the drying agent will begin to clump together. So if, for example, the drying agent is a fine powder, it would then form larger, chunky pieces. So we look for that clumping. We continue to add small portions until we notice that the new portions don't clump, or when we swirl it, we get a snowstorm of the fine powder. At that point then, we stop adding drying agent and we let the solution stand for about 10 minutes to complete the absorption of water. We then need to separate the liquid solvent from the solid drying agent. On a small scale, microscale, we can often just use a Pasteur pipette, very carefully sucking out the liquid while trying not to suck out any of the drying agent. On a large scale, this is impractical, and what we'll generally use is filter paper, and we'll pour that mixture through the filter paper, collecting the liquid underneath and leaving the solid up in the filter. Now, after we have separated out the liquid, what we will see is that the drying agent, the solid, will still have liquid sort of stuck in between it. It'll still be wet with that solvent liquid. Unfortunately, if that's a solution of a desired substance, that amount of solvent that's stuck in the drying agent will actually also cause us to have less of our desired substance. So what we will need to do is rinse that drying agent to dissolve up as much of that substance as possible. So to do this, after we have filtered, we add a small amount of pure solvent back to the drying agent, swirl, remove that liquid again, and combine that with our original liquid that we removed the first time. We call this process rinsing. In general, one rinse is probably enough, but it depends a little bit on how much liquid is left behind and especially how valuable the solute is. Just like with extraction, multiple rinses with small amounts of liquid will be more efficient and can give us much better results than just one rinse. Very often after an extraction, we will want to isolate the solid or liquid solute that's dissolved in the organic layer. In order to do this, what we can do is evaporate the organic solvent and leave the pure solute behind as a residue. It's important to note again that evaporation is not the same thing as drying. In organic chemistry jargon, drying means removing water, but still having liquid left behind. Evaporation means removing all of the liquid solvent by converting it to its vapor, leaving only any solute residues behind. We're going to use a special apparatus for evaporating. It looks something like this. We're going to take our liquid solution that we want to evaporate and we're going to place it into some type of container. An Erlenmeyer flask works very well for this, but if we have a small amount of liquid, we might even just use a test tube. We're then going to place that Erlenmeyer flask into a container of basically tap water. We need that tap water because as we evaporate the liquid, we will also be removing heat energy in the form of the heat energy of vaporization. So the temperature of the liquid would go down, which would reduce the rate of evaporation and even cause water to condense inside. By putting it in a larger reservoir of water, that large reservoir of water will have heat energy which will flow back into the liquid, replacing the heat energy lost in evaporation. Very often, we don't even have to heat the water, but if necessary, we can put it on a stirring hot plate and turn it on to a very low heat. We don't want our water to get very hot, but maybe slightly above room temperature, bath water temperature, can be very helpful. Now, when the liquid is left in contact with the atmosphere, vapor will naturally come off of the liquid because of the vapor pressure. The process of evaporation then involves leaving that container open to the atmosphere so that the vapor will come off the liquid, exit the container out into the larger system of the universe. And because that vapor is now out here, it will not be able to go back down, strike the surface of the liquid, and go back into the liquid. So therefore, the liquid vapor system will never reach equilibrium. This then, kind of by Le Chatelier's principle, as the vapor moves away, more vapor will have to come up to replace it. In theory, we could just leave this open, and over time, all of the liquid would evaporate. This, however, would be very inefficient time-wise, since it might take hours or even days for all of the liquid solvent to evaporate. So we're going to help it. We're going to help it by setting up a tube that is connected to vacuum, which draws vapor in. We place that tube into our container above the surface of the liquid. We want to be very careful not to place it into the liquid, otherwise the vacuum will suck up the liquid like a straw and we'll lose everything. In order to do this, we use a piece of heavy-walled tubing called vacuum tubing, and then we place some type of rigid adapter in there so that we can put it down very far in there and very carefully control the distance to the surface of the liquid. We generally, in this laboratory, make our evaporation adapters out of our plastic syringes. Once the syringes are sort of worn out, we cut the top off, and then that makes an excellent evaporation adapter. We also make sure that we clamp both our tubing and our container for security. Now what will happen is, once we set this up and turn on the vacuum will begin to draw air and vapor from the liquid into the vacuum system, where we have set up a very low temperature condensing thing to collect that liquid, and then there's a vacuum pump. Because we take that vapor away very rapidly, instead of waiting for it to diffuse out of the top of the system, the liquid will then begin to evaporate more rapidly, since it will be very, very aggressively and rapidly trying to replace the vapor that's being lost. This will cause the overall evaporation process to speed up greatly. We just continue this process then until all of the liquid has evaporated, and very often, if we have a solute, there will either be a solid or liquid residue left in the bottom.